Ora si registrerà la conferenza.
Good afternoon to everyone. Today, in this new episode of Science Colloquia, I have the pleasure to introduce to you David Bronte Ciriza, who is a brilliant PhD student working in our institute in Messina. He's a part of the project of in the active matter network within the Marie Curie program. He comes from Navarra in Spain, and he's here now to work on the machine learning applied to the optical forces calculation for the interaction with active matter. And now I leave the speech to David. Please, David, the stage is yours.
Thank you very much, Nino, for the nice introduction. I'm very happy to be here today with all of you. And I think this is a very nice opportunity and a very nice idea to bring all the CNR IPCF researchers closer to each other. So thank you very much to the ones that are pushing this forward. So today I would like to talk about optical forces for the study of active matter systems. I have divided the talk in 4 small sections. First, I want to explain a little bit about what optical forces are. Then I will explain how we can use machine learning to optimize, to enhance these optical forces calculations. Then I will describe very briefly what active matter is and why we are interested in studying active matter systems. And at the end, I will explain one example of active matter interacting with light, which is the optical janus microengine. So let's start with the optical forces. Light allows us to enjoy beautiful views. For example, this is from the theater in Taormina, where we can enjoy the theater and the Etna.
Adesso lo vorrei, però c'è il seminario dell'IPCF.
So I hear some voice in the background. I don't know if, but I will continue. So light allows us to enjoy these beautiful views, but we can do much more. It's not only something that allows us to get information from the environment. There is much more we can do. We can also use it to transform our reality by, for example, applying forces. So if we have a highly focused beam, we can trap from cells, like the ones that constitute our body, to atoms. And this is not all. We can also trap viruses, we can trap biomolecules, or we can even trap 2D materials like graphene. Today, I'm going to focus in the kind of particles we can trap, and this can be explained by the geometrical optics regime. So in this condition, what is geometrical optics? Well, this is the kind of optics we usually study in high school. We can describe the light as a series of rays. And by applying the laws of refraction, for example, we can calculate what is the orientation of the ray after interacting with a surface. So this is valid when the particles are much bigger than the wavelength we are using. If we go to particles that are much smaller or comparable with the wavelength we are using, then the scattering problem is different, and we need to use different approaches. We cannot use geometrical optics anymore. And okay, so now you might be wondering, okay, we understand this, but why light is able to apply forces? And the key point here is that light carries momentum, and momentum needs to be conserved. For example, here we have a focused beam with many rays and a particle in the center of the beam. So this particle behaves as an optical element that interacts with light and may change the path that the rays will follow in the next steps. So if the particle is in this orientation, this position, you can see here, the rays that are coming into the particle look very similar to the ones that are going outside, and there is not really a change of momentum. The momentum after the particle is the same as the momentum before going into the particle. So the net force being applied on the particle is 0. But what happens when the particle displaces, for example, a little bit to the right? Then this particle, which is behaving as an optical element, is making the rays coming outside the particle going a little bit more in the right direction. So there is a component of the linear momentum in x in this case, in the right direction. But this was not in the initial configuration of the rays that were coming inside. This is by symmetry. In X, there was no momentum at all. And outside, after the particle, we have momentum. So in order to preserve momentum, we need the particle to have negative momentum in X. So we can keep the total momentum the same before and after reaching the particle. So there is a force trying to bring the particle back to the center, back to the equilibrium point where the force is zero. And the same thing happens if the particle is coming closer, the source of light, closer to the origin of the beam. The divergence of the light is higher if the particle is closer. So the momentum in the direction of the beam is decreased. And in order to account for this, we need the particle to move upwards in this case, or downwards if the particle is farther from the center of the beam in this direction. Okay, so with this, I hope we can get some insights about why we have forces when we interact, when we make particles interact with light. And one of the problems we face is that if we want to compute the optical force being applied on one of these particles, we need to account for all the rays. And the more rays we consider, the more accurate is the force calculation we get. So with this, we have finished with the first point, optical forces, and now we want to move to the second one. How can we use machine learning to compute optical forces? Well, first, let's start from the beginning. And in our lab, we like light and we love optical trapping. And we use it for many different applications, from the study of interstellar dust to the study of active matter systems. We will talk a little bit more in detail about these active matter systems later on. So we like this, but we were not completely happy because we were facing a problem. If we wanted to compute the optical forces, this was too slow. As we said before, we need to account for many rays. The more rays, the more accurate the calculation is. But of course, the more time we need to make this calculation. So imagine you have a particle which is in an optical tweezers, and you need, in order to predict, to simulate the dynamics of this particle, you need to compute the optical forces at a given position, because the forces depend on the position. And then you need to compute the Brownian motion contribution to the motion of this particle. So you can displace the particle to the next position, but you need to repeat this again and again and again. And if you want to simulate the dynamics properly, the time step you need to consider is very small, and this becomes unfeasible. So if this is very difficult in this case with one beam and one particle, you can imagine how complicated it becomes when we have many beams and many particles, and as it is the case in many active matter systems. So this was affecting us, but it could be affecting others too. The optical tweezers community nowadays is very big, and there are many people using optical forces to tackle different problems. So the big question was, how can we speed up these calculations? So how can we make these optical forces calculations faster so we can study more problems and more in detail? So maybe the first thing we can think about is if we can simplify the calculations. Maybe we don't need to consider that many rays. Maybe we can approximate the potential as harmonic and approximate it as a spring. And this is a good idea for some cases, but we are already considering an approximation. Geometrical optics is, as we said before, it is valid when we have particles much larger than the trapping wavelength in our case. But if we want to consider the problem properly, we should account for the whole electromagnetic theory. In our case, geometrical optics was okay, but this is an approximation. If we approximate even further, we start to lose physical insights of the problem. If we approximate this as an harmonic oscillator, for example, we could never explain why some particles escape from the center of the trap. So this was a good idea, but for us was not okay, because we wanted to study more complex problems without losing the physical meaning of our system. So another possibility is, instead of calculating the forces sequentially at the different points when the particle is moving, when we are simulating this trajectory, maybe we can calculate all of them in advance over a grid. And in this situation, we don't need to compute the forces again and again and again, which is very slow. We just need to look at the neighbors. We just need to look at what forces are close, in which points we already know what the force is, and then we can do an interpolation to obtain the force at a given point. And this is a very good idea, and it works very well in low-dimensional systems if you have only 3 degrees of freedom, for example. But what is the problem? That when you want to expand this problem to a higher number of degrees of freedom, the number of parameters, the number of points you need to store, the number of points you need to keep, grows exponentially with the number of degrees of freedom. So 100 to the power of 3 is something more than acceptable, but 100 to the power of 9, for example, is a little bit more tricky. And this is the kind of problems we wanted to face, accounting for 9 degrees of freedom. So these ideas were good, but for us, they were not good enough because they were not solving our problem. So we kept thinking out something else. And fortunately, we realized that someone already faced a similar issue. And in 2020, Isaac Lenton et al. Used machine learning to compute optical forces. They were studying a different case. They were not in the geometrical optics regime, and they expanded the problem up to 5 degrees of freedom, which for us was not enough, but could be a good starting point. So first, we had to understand how machine learning works. And in particular, our algorithm of interest, deeply connected neural networks. This is an algorithm which is inspired by the structure of the human brain. We have a series of layers, and each layer is made of a given number of neurons. All the neurons in one layer are connected to all the neurons in the next one and in the previous one. So we have the input layer, that is the one that gets the information from the environment. We have an output layer, that is the one that gives the answer. We have a given number of hidden layers in between that are in charge of associating the proper output to a given input. So now the question, this is something generic for any kind of neural network. Now we need to make it our own. We need to teach the network how to answer our question. What is the optical force in a given position for a given orientation and a given configuration? So in order to achieve this, we need to train the network. And we do this by showing a lot of examples. Where we are showing these examples to the network, the connections between neurons are being adjusted. And at the end, hopefully, we reach our final trained model that will be able to associate the proper output to a given input. In our case, the proper force for a given position. So just to give an example, when I first came here to Sicily and I saw granita with brioche, I didn't know if this was good. I didn't know if I should eat it. So my network, as you can see here, it was not trained. I didn't know what to do. So I decided to give it a try. I wanted to check if it was good. And then my network, my connections between neurons started to change. So now that the network, my brain, is trained, when my input layer, which in this case should be my eyes, see some granita in the table, the hidden layers, my brain, tell the output layer, which in this case are the neurons that are connected to my arm, to get the spoon and eat granita as soon as possible. So we thought that machine learning could be interesting. It could allow us to go beyond traditional approaches, and we decided to give it a try to our particular problem. So in our case, we want to train the network for 9 degrees of freedom, accounting for almost all the parameters you can have in a basic optical tweezers experiment. Your particle can be in a different position in the 3D space, so you have 3 degrees of freedom. Your particle can be in a different orientation, so we have another 2 degrees of freedom. Your particle is not necessarily a sphere, it can be an ellipsoidal, so we have 2 other degrees of freedom, and we are on 7 already. And we can also change the refractive index of the particle and the numerical aperture of the objective we are using to focus the light. So with this, we have 9 neurons in the input layer and 6 neurons in the output layer with the 3 forces and the 3 elements of the torque. So we train the network, and now the big question is, how well does this machine learning approach perform? No, we were complaining before that the traditional calculation, accounting for all the rays individually, was too slow. Well, let's see. Geometrical optics can do 13 calculations per second. Our neural network on a CPU can do 280 calculations per second. So we improve the speed by a factor of 20. But if we can use the GPU of our computer because we have many particles or many beams, or we just want to repeat the calculation many times, we can go up by another factor of 150. So in total, we can achieve an improvement in speed of a factor of 3,000, which may just look like a big number, but with this, we can do in 1 second what used to take 1 hour, or in 3 hours, what used to take a year. So this is, we were very happy with this because we solved our initial problem. Our neural network was faster. But of course, this is not enough. We want it to be fast, but we need it to be accurate. So how accurate are these calculations? Well, let's see. For example, this is the geometrical optics calculation of the torque in Z at a given position in the 3D space for a given particle with a given refractive index. And you can see here that there are a lot of artifacts. These forces, these torques, are not as smooth as we expected. And this is happening because we are considering a limited number of rays. We have 400 rays, which is not the case of real light, but we need to discretize the input to our computer. So this is a problem that geometrical optics is having. The more rays we have, the less artifacts we have, and the better the calculation is, but the more time we need. So let's compare this geometrical optics data with the neural network prediction using this bad data to train. And we can see how this prediction, at least, is much smoother. And if we do the difference, we subtract the prediction of the neural network to the geometrical optics calculation, we see how we are removing these artifacts that were coming from the geometrical optics discretization. So this is just for a given plane, but if we do the same for a lot of planes, we are moving this plane set now in this video, you can see how it's always the same situation. We have a lot of artifacts in geometrical optics that are being removed by the neural network, as you can see in the last plot. And if instead of looking at the plane, we just look at a given section, we see how when geometrical optics is using 400 rays, the torque is very noisy. This is not, well, this is not noisy, it's not random, but we have a lot of artifacts. If we increase the number of rays, the calculation becomes much smoother, even though it requires more time. But when the neural network is trained with the blue data, with the data with not so many rays, we can see how it clearly overcomes the initial quality of the training data. So in this case, the student, which is the neural network, is getting much better than the professor, which is the original geometrical optics data that has been used for teaching. So with this, we were very happy because we are not only faster, but also more accurate than the traditional method. And now I just want to show a few examples about why or what are we using this for. One thing I have been working on lately is the study of the motion, the dynamics of an ellipsoid in a double trap. The same problem we were saying before, it was difficult because we need to do this for small time steps. So here you can see how the ellipsoid is moving. At some point, it goes from one trap to the other. And if we study this system with a little bit more detail, we can see, for example, how the equilibrium position of the particle depends on the aspect ratio of the ellipsoid. The equilibrium positions come closer to each other when the aspect ratio of the ellipsoid is larger. We can even find some different equilibrium positions between traps. We are only having 2 traps, but we have 2 equilibrium positions. And if we play a little bit more with this by using, for example, 3 beams, with 3 beams, we can manage to get 6 different traps, even though these ones are much stiffer, much stronger than the ones in between. So this was one example. The other example we are working on is to study, for example, the possibility of optically sorting red blood cells with this neural network trained with different data, but we can simulate the motion of a red blood cell in an optical tweezers setup. If we are able to study how these dynamics of the particle, how this trapping changes for different red blood cells that might be affected by some diseases, we can think about optically sorting healthy from unhealthy red blood cells. So with this, we are done with the second point of the talk. And now I want to explain very briefly what active matter is. So active matter. These systems of elements that consume energy in order to move or to exert mechanical forces. This definition is very broad, and there are so many systems that can fit in this definition, from the flock of birds, as we can see here, to a school of fish, to a group of sheep moving from one place to another, to a collection of bacteria, or even to us humans. We are eating breakfast in order to get energy from the food so we can move or exert forces. This is what active matter is. As you see, this is very broad. And why do we care about this? Well, it's all around. There are so many systems we can study as active matter just because of this, because of the definition. This is very broad, but there are a lot of systems that fit inside. It also exhibits some very interesting phenomena. For example, motility-induced phase separation. If we have particles in a gas state, they are just moving from one place to another, and when they collide, they just have an elastic collision and they go away from each other. They don't keep in the same position. They don't keep being close to each other. However, if we have an active matter system, if we have particles that are being propelled in one particular direction, when two particles clash into each other, they will remain there pushing each other until their reorientation time brings them far from each other. And this produces what we call motility-induced phase separation, which means that if you have a system with active particles, the phase transition from gas to liquid will come earlier just because of this, because these clusters will be produced easily. You don't need to achieve a high density, but just the level of activity can make this transition easier. In this image, you can see how the color represents the orientation. So these ones here in purple are with a velocity, with a propelling velocity towards the left side. And these are keeping all these clusters together, because these ones which are yellow, for example, they want to go towards the right, but they cannot escape because they have these blue ones propelling against themselves. And we have the disorder we were expecting in the middle of the cluster. But we have two walls just that are naturally formed and that are keeping the cluster together. And the last thing why we are interested in this is because it has very interesting potential applications. For example, in drug delivery. This is a little bit of a futuristic picture, but if we have systems that are able to take energy in order to propel themselves, we can use this, for example, to carry some medicine to a given part of our body. And once it reaches this part, we use, for example, these properties in order to cluster around the affected areas. It could be something very good for us and for our health. So we wanted to study active matter systems in presence of optical forces. We want this active matter field that was new to us, together with these optical forces that we are more experienced, we wanted to put them together. And for that, we wanted to use Janus particles, which is a very common system to study artificial microswimmers. We have not necessarily a sphere, but a shape which is made of two different materials. So the properties of B are different to the properties of A. So for example, if there is a chemical reaction that is producing some bubbles, we can have some propulsion in this direction. This propulsion mechanism is not necessarily chemical, it can be also thermophoretic. For example, if A is heated more than B, we will observe how the particle starts to move in one direction. So with this, now we know a little bit of what active matter is, why we are interested in studying active matter, And now I will talk very briefly about our optical janus microengine. So if we have a silica particle close to an optical tweezers setup, close to a highly focused beam, we know that the silica particle comes to the center of the beam. However, if this silica particle is coated with gold, which reflects light, the particle will fly away from the center of the beam. It will not remain in the center, but very far. We'll try to escape as far as possible. So in our case, we have a janus particle. The question we were asking ourselves was, what is going to happen? We have a particle that half of it wants to go to the center of the beam, and the other half wants to escape. This is a situation we encounter many times also in our daily life. We are with a friend, with someone else, and we don't necessarily agree. But how do we find a solution for that? Well, I don't know how you do it, but the janus particle gives a very interesting solution. And we were surprised when we observed that the particle found a position of equilibrium in between. It doesn't go to the center of the beam, which is here in a purple circle, but it neither goes far away, but it remains at a given distance, diffusing in the angle. And what was even more surprising for us what happens when we change the polarization of the light. In the previous case, the particle was moving. In the previous case, the light was linearly polarized. Now we wanted to make it circularly polarized. And what we observed is that the particle starts to rotate in a given direction. So we are transferring this angular momentum from the light to this orbital angular momentum from the particle. And if we change the sense of polarization of the light, we can also change the sense of rotation of our particle. As you can see here, where the particle now is rotating clockwise. You can see how repetitive the motion is. The trajectories are almost overlapping with each other. So this was our situation where we can control the sense of rotation with polarization, but this is not all. We can also control the radius and the speed of our microengine. This depends on the power of our laser. For higher powers, as here in pink, we have trajectories with a bigger radius, while when decreasing the power, the particle comes closer to the center of the beam. And you can see how all these trajectories are almost perfectly concentric. So if we plot the radius, you see again how the radius grows with higher powers and how also the velocity, the linear velocity of the particle grows with the power. So we were also very happy with this because we think can hold some promising applications. And to increase our understanding of this, now we want to use the neural network to study what is the contribution of the optical forces to our system. With the speed and the accuracy of the neural network, we should be able to do much more simulations and hopefully get some more insights about why we are observing this phenomena. And this is currently something we are working on, using machine learning to perform these calculations. So just as a conclusion, we have explained that we can use light to apply forces. The calculation of these forces can be improved by using machine learning, both in terms of speed and accuracy. And this is what we can see in the picture. For example, here, this is the calculation with geometrical optics, with these many artifacts that look very fancy. This is with neural network. And again, the same kind of picture as we saw before. In this case, we are subtracting this to this, and we only see the artifacts have these very beautiful shapes. And we have also explained what active matter is, why these systems are important for us, and what kind of applications could they be used for. And we have explained how combining optical forces and active matter research allowed us to reach this optical janus microengine. So with this, I would like to thank all the people involved in the things I have been showing here. for example, the Giovanni Volpe's group in Gothenburg University, the group which have been involved in the machine learning part, also the group of Luca Biancofiore in Wilken University, who we are collaborating for the janus particles we are using for the optical janus microengine, and also the group of Phil Jones in UCL in London, who we are collaborating for the study of the optical forces in red blood cells, in particular with Riccardo Tognato, also from Italy. And of course, I need to thank also the funding and our beautiful group here in the CNR IPCF in Messina. Also, thank you for your attention and for your time. And if you have any questions, I'm very, very happy to try to answer. If you want to ask them now, perfect. Here is my email if you have further questions. So thank you very much.
Thank you to you, David, for your beautiful talk. And now I will stop the registration.